Welcome to the stress tensor. We know stress represents forces of interaction across surfaces in a continuum. We will write out stress as a tensor throughout the biomechanics experience. However, what are we really looking at when we see that tensor? You may be wondering what these numbers represent. To be able to really see what is going on, we need to expose the forces of interaction by looking at a surface within the body. Let's draw a simple, infinitesimal body in this coordinate system, like this cube. Picture this being a tiny, tiny cube inside an organ tissue, for example. We will have 3 stress components associated with each direction on face 1. These are the components of T1. Then we will have 3 stress components associated with each direction on face 2. These are the components of T2. And finally, 3 stress components associated with each direction on face 3. These are the components of T3. Notice that we have now drawn all 9 of the stress tensor components. This should help you better visualize what each component from a stressor tensor means. Notice also that there are components on the other 3 faces of this cube, but they should be due to equal and opposite tractions, which would make these components negative. However, since they are acting on negative faces, they are also positive stress components. This allows the forces and moments to balance on the cube. Notice also the way we labeled each stress component. Sigma ij refers to I as the traction component. Think of the face we act on. And J refers to the direction of the stress component. So sigma 2, 1 acts on face 2 in the direction of E1. Components on the diagonal of the stress tensor are normal components of stress, while components on the off diagonals of the stress tensor are shear stress components. Now that you understand where each component comes from, let's understand the math behind all of this. Think of a general surface within a body B that is undergoing stress. We can draw a unit normal vector to that surface, which is basically an outward normal at a point on the surface P. Stress will be defined by the surface forces, which are forces of action across the surface in question. These forces act on the surface due to all of the surrounding material. Think of organs all touching each other. Keep in mind that these forces are different from body forces, like gravity, which act at a distance. At the point P in the continuum of the surface, there will be a force of interaction. This force is what we call the traction. This force of interaction at the infinitesimal point P and the normal vector at that point will together help to find the stress at that point. The traction vector will not coincide with the normal vector to the surface, except in some very special cases, such as when the stress is in a pressure field. However, in reality, a component of the traction is normally tangent to the surface. Since we deal with 3D bodies, we will incorporate some more complexity into this concept. Consider 3 unit base vectors, E1, E2, and E3. They define the outward normals to 3 mutually perpendicular surfaces. Think of the 3 coordinate planes. We will consider a traction vector Ti as the vector acting on the face normal to EI. This is the relationship that relates the two. Sigma ij has the components of the second order stress tensor. We can rewrite this relationship by playing with the index notation. Don't worry if you don't understand this as of now. There will be a video on it. So this is another way to state the relationship between the traction vector, the normal to the surface, and the stress tensor. For reasons that we will discuss more in other videos, this stress tensor is also called the Cauchy stress tensor, which is the real or true engineering stress. Now that you have a better understanding of what the stress tensor means, we can start tackling some examples. I will see you next time.